Hello community! Although it is freezing cold outside in the Austrian Alps, we have today a hot topic. Is there something better than a RAG system? We have some new idea and some new research paper, so let's have a look. Now, I want to explore here two solutions in parallel, because why not? So, at first we have our LLMs, and if we go to continuous learning of LLMs, we encounter significant problems, because normally we train our LLMs on one dataset for a static environment. With RAG, we encounter RAG is not secure, because continuously updating RAG and new indexing and everything is so expensive, and therefore quite a lot of RAG systems are out of date. And with our LLMs, even if we start multiple fine-tuning, this will lead to catastrophic forgetting from the pre-training dataset. So we have two main problems, and we will try to solve them in one new solution. RAG is not secure. I know everybody who is doing RAG will disagree with me. So therefore, just read December 24, 2024 here, the pirates of RAG. Adaptively attacking LLMs to leak here the knowledge base and crack open the RAG system. A beautiful paper if you want to understand how the mechanism works. Or if you go a little bit back in time here, February 2024, a basic foundational paper, The Good and the Bad, exploring privacy issues in the RAG system, and it is still valid today. Now, of course, the insecure matter of RAG is inherent to the retriever itself. It is not just a feature we can get rid of, it is the system itself. Because you remember, if we have here a vector embedding in, 768 dimension, and here this vector is encoded vector representation of this semantic content, how to analyze medical data, and right next to it we have the medical data of Mr. Green. If I do now here a similarity measure, a close by metric, and I have here cosine similarity and I calculate this, if I have my query how to analyze medical data, maybe I get back, if this is happening, the private medical data of Mr. Green. This is an inherent feature, and yeah, I know there are a lot of different possibilities and we can try something, but this is an inherent feature, how the data are vectorized. Therefore, please have a look, Pirates of the RAG. I think it opens up your eyes about how open RAG is and how I can extract, without having access to the database, via RAG private data. But we were talking here about LLM and RAG, and we want to focus now a little bit here on LLM, why we will have catastrophic forgetting if we have continuous learning. And this whole video is focusing not on just one fine-tuning, one alignment. No, we have continuous new data coming in every day. And every day you would have to fine-tune your LLM on a new huge set of training data. So this new idea here, also from Intel, is we have now a second object to our LLM. We do have here an adaptive filter, and they call it an External Continual Learner, ECL. And this ECL module tackles here the challenge of enabling AI models to learn sequentially from new data and new tasks without forgetting what they previously learned. So if this would work, this would be amazing. But how is the system working? What were the original idea behind this? Now, easy. If we think about the process flow, we have a user query, and it comes here into this external module. And in this external module, something happens, because now we have a modified in-context learning prompt is now generated by our ECL, and we have a modified ICL with a reduced complexity, but with some additional information provided to the LLM, where the new learning happened already here. So this LLM here, this primary LLM, is, if you want, we're not touching the learning weights at all. The model stays as it is. The new part is here really here a dynamic external continual learner module. So no fine-tuning of our primary LLM. This is great. We can use some right off the box LLM that are quite expensive, but we don't have to fine-tune them. Imagine what you have to pay OpenAI to fine-tune here the O1 model. With this dynamically adapted filter, this becomes now interesting in its implementation. And if you are mathematically sound, you know, a Gaussian modeling here of a class distribution with a specific distance really effectively captures here in a non-Euclidean matrix space class here the relationship to this module. If not, are you interested to understand this methodology? I was. So here we have this new research paper by University of Illinois Chicago, Intel Lab USA, and Salesforce EI Research USA. And they published this on December 20th, 2024. And they talk now not about in-context learning, but in-context continual learning. So ICCL. Highly interesting because we have completely new data coming in every day if you are Salesforce or if you are Intel. And we can't train our LLMs every day. That's impossible. That's too expensive. So what we do, we are facing now a continual learning process that aims to enable our LLMs to learn a sequence of new tasks incrementally. So let's see how we do this. If you want to understand CL, this is the paper I would recommend. This is from April 2021, but it has some beautiful insight. And they said, hey, there are 3 categories. We have this task incremental continuous learning. Then we have the class incremental learning, the C-IL. We're going to talk about C-IL today. And then we have the general domain incremental learning. But let's focus on the class incremental learning since this is our topic. Now, if you have a look at this publication from June of 2023, the learnability and the algorithm for the continual learning, we have a real problem, especially in the inter-task class separation, which refers here to the phenomenon that without accessing the previous task data, the learning of a new task has difficulty in establishing here clear boundaries between the new and the old classes. So there's a whole complexity of unsolved mystery how to do this. And I think this is the best paper if you want to have a little bit of a deep dive, also a little bit of a mathematical deep dive into this particular topic. And we're going to talk about this. And I thought, you know, in my simple mind, with my simple brain, I thought, hey, I just retrain my LLM with every new bunch of data. And then I fine-tune my expert LLMs and my expert agents here with every new data. And I update my vector embeddings of my old data with the new semantic similarity here and a new BERT update of the vector representation of the new data. And then suddenly it dawned on me, even if I do this every week or even every month, I have about 800 scientific publications per day coming out. So the amount of new stuff, I mean completely new stuff that is not in a vector store embedding is huge. So I said, okay, now we understand why Intel is looking at this. So what is the secret? How do we learn continuously with our AI systems? This is the beauty of this study here by Intel, Salesforce, and University of Illinois here. They call their system InCA, so in-context continual learning, assisted by an external continual learner, plus a secondary LLM. I will not destroy your enjoyment if you want to read this study here. I just give you here the main sort, the main ideas, the concept, and how you do it. But there's so much in this study. Please read it. So let's start. This is the general flow. No? User query, external continual learning, an adaptive filter, does some modeling, constructs a new in-context learning prompt for continuous learning. And our main primary LLM has not been fine-tuned on any new data and is able to solve the task. This is here the overview of the InCA framework here from Intel in their visualization. But, you know, I think it's much easier if you just think about how is it different from a RAG system. I think it will open up your eyes. So in RAG you have, hey, when will my next check be deposited here in my bank account? So what you have here with RAG, you have a vector space, a vector store, whatever you have, and you have encoded here the semantic information of this query is now positioned somewhere in a query vector, and close in the mathematical space of this vector space, we have other objects real close by, a similarity measure, cosine similarity to my query vector. Now, if I look now here in my RAG system, here to those vectors, I want to understand what is the information in this vector, and the information encoded is here. Payday for Mr. Green in August was the 12th, for Mr. Green in September was 11, Mr. Green in October was 14, and Mr. Green in November was the 8th. So this is now the reply from the retriever that it gets out here of this vectorization of this vector representation of the data. RAG will provide these answers back to my primary LLM. But what should the LLM do now? You can calculate a mean, or you can calculate, some data distribution, maybe if you have more data. But you see the problem inherent to this? RAG just returns something that is, you can't decide what will be in our current month here, the date when you will get your paycheck. And let's have now a look here at the process flow in this new methodology in InCA. And here you have it now in total. So we start here with a raw text input. This is my customer query. Then we have a tag generation. So a secondary LLM generates now a set of relevant tags, and I will show you this in a minute, for this particular customer query. This is task specific. And then I build a class representation. So each class is statistically characterized using now the tag embeddings. Embeddings, vector representation. The Gaussian parameter for each class represents the statistics of embeddings derived from the tags produced for training data sample of each particular class. Now comes the moment where our new ECL module starts its adaptive filtering. So when a new input instant comes into the system, now the distances between the generated tags of this input is measured by a particular complex distance and is simply compared against all the class distribution that were created in the previous steps. These were the mean vectors of the tag embeddings. So whenever we have something new coming in, we want to compare it to the old stuff to find out we already know this, we already have encoded this, or hey, this is something completely new, we have to take care about this, that we do an embedding of it. So then the closest, let's say top K classes, the top 5 answers are then selected along, given here this particular distance, this close by distance, along with their class summaries to be included in the new in-context continuous learning prompt for the prediction now by our primary LLM. Then we do have the in-context learning with the class summaries. Make here the class prediction by including here the selected class summaries, the top 5. We include this now in our new ICL prompt for continuous learning. And then the primary LLM will now predict here the class membership based on the information that is given in this single prompt. So what we have in our new updated ICL continuous prompt, we have here the text input, my customer query, the top 5 class summaries, the top 5 classes itself, and previously seen class names. At this moment I noticed something, because have you also noticed that we move now from a singular data point in our RAG system, in our embedded vector, that represents now singular facts, that we move now to a higher level, a tag. And this tag, if you want, acts like a meta object, no? Kind of a generalization. Because the single fact was the medical, data for Mr. Green. But now we move to tags, and tag represent here a higher complexity level. So we in InCA now moved inherently away from the private, detailed personal data that were encoded in the RAG system to be retrieved fast from our vector store. And we don't have any more this private data that we need to answer the query. Let's have a look at this in an example. Let's say you have a customer service desk or a telephone or whatever you have. No? And let's say for simplicity, we only have 3 specific classes. You want to make at a bank a direct deposit. You want to know when is your payday, and you want to get your account balance. So with these three classes, these are the processes of the company bank office. So my query is now, when will my next check be deposited here in my account? And this is very similar to the RAG example I've shown you, because I want to make it clear what is the difference. So first, we have a secondary LLM that generates here tags. And the tags may be payday, deposit, check, banking, date, funds, transfer. And then we have classes. Classes, we'll show you later how we build classes. We have now a class direct deposit here. So the training data of my secondary LLM, we had many inputs with this direct deposit class with tags such as account, deposit, paycheck, yes, whatever. As InCA now learns, the statistical mean vector of the class is calculated as the mean embedding from all the generated tags from the training example for this particular class. And those tags will be represented by embeddings in a high-dimensional vector space and mathematical space, which are then combined together with a simple average operation. Simple task. We know this. This is here a classical, if you want, embedding here of some semantic or private data. As I told you, we have three classes. Then we have the class payday. Here you have the description of payday. And then you have the class account balance, and here you have the tags for the class account balance. And then the ECL class filtering is just telling us, hey, what is the most probable class that we should put into our continuous ICL prompt for the primary LLM. You have all the tags. The tags are now embedded in a high-dimensional vector using the same SBERT encoding model. I have 50 videos on sentence transformer model, how you build your own on your own domain-specific data with your own instruction data set. And I have also a new video on the modern BERT. So there's plenty of videos to watch if you want to build your own SBERT encoding model. And then we have the class embedding vectors. Yeah. This particular kind of distance here is a little bit different because it is here what we call a centroid, or here an overall mean for multivariate data. So let's look at the in-context learning prompt construction itself. InCA will now use summaries from payday and the direct deposit. This is the second most relevant class, and the original user prompt, and construct now the prediction prompt for the primary LLM. And here you have it in blue. So we build now, hey, based on the given query by the user, classify the user's intent into one of the following categories. And now, like in RAG, where you have with the retriever, you retrieve 200 different vectors. Now we go with 2 or 3 different classes that have a higher abstraction level. And for these classes, we provide the class summaries, so that the LLM, the primary LLM that has to do now the decision, which of these 2 or 200 classes is now the correct class for the user query, has enough data on it. So this was the user query. When will my next check be deposited in my account? And now predict the class. So we hope now that the primary LLM will identify that this input here, this query, belongs to the payday class, and only to the payday class. And you might ask, what do we achieve with this? I'll show you in a second. So, terminology. Tags are semantic descriptors. They capture the meaning of an input text. Classes are more or less labels. They represent the output category. Tags form class embeddings. The distribution of the tags and their embedding in a mathematical vector space are used to form a statistical class representation for each class that is created from the previous inputs. We have incremental learning happening with a lot of statistical background. Our ECL filter is based on the tags InCA uses here to calculate the distance between the current test instant tags and the class statistical representation to pre-select the most relevant classes. I've just shown you the example. So if you want, tags are crucial. Tags are here the semantic bridge connecting here the raw text data to the class representations. And they facilitate here the modeling and the processing here of the class-specific patterns in the text that we ultimately try to use in this classification procedure. I told you this is kind of a higher complexity system. And reading here the publication by Intel, I always thought here about the latest publication by Meta here on large concept models. And I thought, can I show you that somehow there's the same idea behind this by Meta and by Intel, but I think this would be too complicated. But if you want, have a look at this video, then you see LCM, and maybe in my next video I will reflect here on the different views that Intel and Meta have on this new trend to optimize our former RAG system. Now, talking about classes, talking about tags, and I told you tags are here the semantic bridges. How do we get to our tags? Now, simplest way, we use an LLM. Yeah? Here you are from the original publication by Intel. Here, prompt, this is the prompt, the guidelines, topic, keywords, related task. Then here, examples given, and then the LLM tells us, give them a user query, a specific user query, the task the LLM could identify. For the example section, here from the original paper, here you have all the different examples that were used by Intel, Salesforce, and University of Illinois. So let's have a look at the complete picture. What we have is now an external module, this External Continual Learner module, ECL, that is a pure statistical and mathematical processing module. This is not an LLM, careful. We do have a secondary LLM that could be, if you work in this domain, and you know that this is also a specific LLM that is trained on your domain, you can have this identical LLM for just providing the tags. So you have here the user prompt goes into the LLM, and the LLM, I just showed you the specific prompt, gives you now back the specific tags. And then you have ECL and ECL filtering, adaptive filtering, and so on. And then what we have after this filter, we have a new in-context learning and in-context continuous learning prompt. Creates a final prompt. We have the original input query, the names of the selected top 5 classes, and a concise summary of each selected class. So we moved away from a particular SQL query for a particular amount in your bank office to a more general category. Then this ICL prompt is constructed by our AI. The structured prompt is passed now to the primary LLM, and this process simply uses the in-context learning principle that we know, but now added with some additional, if you want, hierarchical, higher complexity level content that the LLM can now learn new incremental classes. And then the LLM does a simple task, a class prediction. The LLM then predicts a class that is given the input instance, that the given input instance belongs to. So you see, all this new incremental learning is happening here on the right side. We can use any LLM without any additional fine-tuning, without any additional continuous training. And this is, I think, the beauty, and this is what I think why Intel did this, because the idea that you can use any LLM, if you just have here this heavy in-context continuous learning prompt with all the information, then the LLM should be able even to compute new data. Great. Now, does this InCA need RAG? The key point of the publication is no. There's no need for some external information. Why? Because we work on a purely statistical mathematical model, a brand new model, but a highly intelligent model. Let's talk about it. InCA addresses here the problem of the prompt scaling here by intelligent filtering with an external continual model rather than gathering external content. So there's no external knowledge base required. The RAG's core mechanism is retrieving relevant content from a knowledge base. And in contrast, InCA does not need this extra resource. And you have a replay for your architecture. So where are we now? So I have a user query, and now I have here a new InCA class classification task. And now how do I come to my task solution? Now, simple, a direct answer. Some classes might map to a direct answer. So if a client asks for a current bank statement or bank balance or whatever it is, a direct retrieval from a customer database would answer this question. SQL, but you don't need, and this is important, not a RAG embedding. You don't need a vector store. You just have here a functional calling, an API call, a SQL call. This is all you need. You don't need anything anymore because we have already done this before if we use the new InCA. Scripted response or a task flow based on the class that we have now from the InCA process, a correspondent scripted response may be generated. Activate the Python environment, start my IDE, or a task-oriented workflow that is real task-specific can now start. Start Prolog and code this in a way that I can find here a better causal reasoning performance of my LLM. Other examples. Credit card application. Start an interactive dialogue to fill out here an online application. Or if you want to transfer funds, start a task flow where you get confirmation from the user to perform some operation, or maybe you need some passwords. Or you can deliver some based explanations or links how to do something that are already predefined. So the first key part is that with the correct class prediction that InCA does, InCA provides now the contextual understanding of a client's request. And this is beautiful because imagine you're a company and you have now 1,000 clients queries coming in parallel. You have established processes in your company. You can't invent suddenly 10 new processes in your company. You have to map all your clients' query to your established processes in your company. You can build 100 AI systems here, but the processes are defined and the interaction take place, and you see, it's a predefined company system. We will talk about here a more flexible approach in the industrial production a little bit later on. So the main idea is that by predicting the correct class with this InCA methodology, the system can now initiate a highly specialized workflow that is tailored now for each particular class without using here some generic all-purpose methods or AI system or some prompt engineering by Anthropic or OpenAI or Microsoft. We can do this for our task, for our company, for our specific classes. And after knowing what kind of request the user is inputting here, the methods are specialized to respond to each particular class. And you can invoke this, and the complexity now of the overall action can be decreased significantly. You don't need an AI system that understands everything about every class possible in this world. You've broken down the complexity to the processes that are established in your company, and you can identify processes that you need to establish in your company a little bit later on. Let me give you an example. Imagine you have an airport information desk, and it's holidays, and you can imagine what happens without this system. So let's say you have an AI information desk. Now, everybody is putting an input and you have long description. People tell you what happened to them. And a poor single eye has to do now everything and find solution to everything. There's a high chance that the chaos will overrule this AI system, causing here some performance decrease. If you have this new system with this adaptive filtering, it's like in a sophisticated system that quickly sorts each customer query into different classes, like baggage claim or check-in or lost item or flight information or transfer to different flight or whatever. And then our second tier, our other agents now of the airport can now jump on their special task. And their agents have been built for one task only, let's say lost item. And those dedicated expert agents can now perform the task real fast. But they only get the lost item tasks and not a flight information task. So you see, we reduce the complexity, make the agents smaller, faster, and cheaper to run. You remember the system here with the RAG? Imagine this in our new InCA system. We have here this query coming in, and let's say we have now the class payday identified. And here's the description by the AI, what is the payday? And we built the ICL and the LLM says, hey, great. So I get this and I now have to decide which class it is. And I have here my agent 1 to my agent 4. And I have, this is an AI agent with an LLM and this is an AI agent with an LLM. But if I have a simple question, hey, when will my paycheck materialize here in my account? If there is a simple solution, I don't have to use an AI. I can use a simple rule-based system. I say, hey, if I understand that the payday of this particular company is the 22nd of each month, but if this is a Saturday, the transfer will happen on the next Monday. And if the 22nd is a Sunday, the transfer will happen on the next Tuesday. And therefore, we can now explain all the deviation that is happening here without applying any AI system at all, because we understand the mechanism behind of this. And calculating here a mean or average or whatever distribution is pure nonsense because there is rule-based. So I don't need any AI. If I have this, I can find my answer immediately if I know exactly what class is it. And linking now, knowing the class, linking the task now to this particular agent, it doesn't need to be an AI agent. Therefore, it is cheaper, it is faster, it is more precise, it doesn't hallucinate. Win-win-win situations. So this incremental learning with this InCA methodology by Salesforce and Intel and University of Illinois is elegant, beautiful. But it is not as simple as I've shown you. However, it avoids the complexity of retraining or storing here with RAG all their data, terabytes of vector stores, by distilling here the class information into statistical parameters, and then you update step by step as new classes arrive in a continual manner. So you can continue to learn, and the system will continuously learn, and this is what you want. You don't want to retrain the LLM. You want to have one LLM that is capable of doing some general task, and then in the in-context learning prompt, you want to provide all the information that the system can now handle new data. Now, this incremental learning in this InCA methodology is a little tiny bit more complex. Let's have a look at this. Begins with representing each newly encountered class through a statistical model derived from its associated tag embeddings. I showed you the secondary LLM. If we have now a new class J introduced, the system employs here this LLM to generate a set of descriptive tags. I showed you the prompt for this from its training data. And each tag is then encoded into a high-dimensional vector in our new vector space, a new mathematical space, using here the pre-trained S-BERT model, where we trained on our domain, like theoretical physics or mathematics or organic chemistry. We trained here domain-specific BERT models, sentence transformer models. Those sentence transformer models generate vector embedding of a semantic content. And the class-specific mean vector, mu, is computed by averaging all the embeddings for the generated text, where R is the total number of generated text, and we have a mean vector. And this summarizes here, if you want, the semantic center of the class J within this new mathematically calculated embedding space with our S-BERT model, and will be incrementally learned when new classes arrive. So we have the mean vectors, and the mean vectors are important, but we need another statistical tool. We need another statistical element, and this is a covariance matrix that we can share between all our classes in our mathematical space. Why? The InCA framework employs here a shared covariance matrix to model the relationship and the variability between the tag embeddings. We want to know the variability of the tags when we add new classes, how they move together. So when a new class K, let's say, is introduced, its contribution, delta K, to a shared covariance matrix is calculated based on its tag embeddings and its mean vector. So the current shared covariance matrix, after processing now the class K, denoted by whatever is updated by using here the previous state, and the new contribution, given here a new mathematical formula, And we have now our incremental approach, and this ensures that we update our covariant matrix step by step. Gradually, it evolves as our AI system encounters now new classes in our input. And the beauty is, the absolute beauty is, we don't have to store them without storing the previous data instances or embeddings for previous tasks, thus making here InCA replay free. And this is one of the main points. It is fast, it is computational fast, and we don't need a lot of storage. This is beautiful, and I understand why Intel was in the team. So what we have now the mean vectors and the incrementally updated, for our continuous learning process, our incrementally updated covariant matrix together form now the statistical descriptive functional of all the classes in our system. Continues every time a new class appears, we do the same stuff. Beautiful. And then our external continual learner selects now the k most relevant classes from all the, let's say, 2,000, 10,000 classes, using here the specific distance between the inputs tag embeddings and each class's mean tag embedding vector, using here the current actual covariant matrix, thereby enabling here targeted and efficient in-context learning through a concise prompt that includes here the top 5 class summaries. So you see, interesting how they built this. So we have only the mean vectors and the incrementally updated covariance matrix, but in a statistical clever way in our vector space that we built with our S-word domain-specific algorithms. And now we don't store the data in detail. We work on a statistical level like LLM and autoregressive system. So if you're not sure, short detail, mean vector, this is what it does. This is the definition of the mean vector. And why we need a shared covariant matrix. Here I summarized this in a short text, what it does and why it is so important here for InCA. You see here it encapsulates, this is the main sentence, the information about how much variation or spread exists in the tag embeddings across all the classes seen so far. So you see, this new incremental learning procedures allows now this new InCA methodology to avoid catastrophic forgetting, as only class parameters are incrementally updated without changing the parameters of our primary LLM model. And I think this is beautiful. This is really, the idea is great. And we have benefits from this implementation, like a minimum storage footprint, because we don't store the real-time data. We have a better computational efficiency because we only work with incremental updates to the mean vector and the shared covariant matrix. There are just some minimum calculation compared here to a complete fine-tuning, redoing of the complete LLM. It's scalable to larger class sets, as I told you, and we have a faster inference, and I have some video on some new inference methodology. So the circle here closes itself. So this is a beautiful idea on so many different levels I can't explain right now. So there you have it. A first introductory video to the new process here, ECL with a secondary LLM that might outperform here the classical RAG system, because this ECL, we have looked at a class prediction task here, is so much better. And if this ECL needs really some specific data, like, I don't know, a specific financial notation at a specific time, you just have here a function calling here to a database, and you do not need the embedding in a RAG system, which is so much faster and so much easier. But the intelligence of ECL, as shown here, if you read the original paper by Intel Salesforce here in University of Illinois, it outperforms the other system. So ECL, the new power tool for you. Maybe you should have a look, maybe read here the complete study. Maybe for your particular case, for your particular task, it might prove to be much more powerful because it has the ability to continuously update its learning. It can learn continuously from new data, which is not available with RAG. Plus, here we build a much more secure system. But more about the security, maybe in one of my next videos. So, if you like this video, if you had a little bit of fun listening to it, maybe you had some new ideas, maybe you want to become a new subscriber, it would just be great to see you in my next video.